Hello everyone, and welcome to this challenge question walkthrough for Edexcel's Core Pure Year 1 textbook, Chapter 6. For our first question, we're told that a 2x2 matrix A has a property that A squared is equal to the 0 matrix, which is just 0, 0, 0, 0. And we're asked to find the possible matrix A such that for part A, at least one of the elements in A is non-zero, and for part B, all of the elements in A are non-zero. Okay, so I guess we can start by saying, well, we can let A be a general matrix with elements A, B, C, and D, and then just find what A squared is. So A squared, we're going to multiply this matrix by itself, and using matrix multiplication, you should get this is equal to A squared plus BC, AB plus BD, AC plus CD, and BC plus D squared. And remember, we're looking for this to equal 0, 0, 0, 0. So we can just equate each of the elements here to get A squared plus BC is equal to 0, AB plus BD is equal to 0, AC plus CD is equal to 0, and finally BC plus D squared is equal to 0. Now instantly I can see these two middle equations here I can factorize to get B lots of A plus D is equal to 0, and C lots of A plus D is equal to 0. And for these equations to be true, we either need B to equal 0 or A plus D to equal 0. For this bottom one, C to equal 0 or A plus D to equal 0. And because we're looking for a matrix A with non-zero elements, I think it's a good idea to, instead of letting B or C equal 0, to let A plus D equal 0, and then both of these equations are satisfied. So just an example of values we can give A and D. To keep it simple, we can go for A equals 1 and D equals minus 1. But there are many different values you could choose here. Just to keep it simple, 1 and minus 1 to us fine. Okay, now looking at the first and the bottom equations now. If we plug in our values for A and D, the first equation gives us 1 squared plus BC is equal to 0, and the last one gives us BC plus minus 1 squared, which is also just 1, is equal to 0. So these are actually the same equation. And all we need now is for BC to equal minus 1. And again, we're looking for non-zero. And again, this could be a number of different pairs of values for B and C. But to keep it simple, let's go for B equals 1 and C equals minus 1. And now we have values of A, B, C, and D, which will give us a matrix A, whose square is a 0 matrix. And actually, all of the elements are non-zero. So RA is equal to 1, 1, minus 1, minus 1. So that's our answer for part A and for part B. Okay, now the next question is from exercise 6C. For part A, we're asked to find all the possible 2x2 singular matrices whose elements are the numbers 1 and minus 1. For part B, we're asked to do the same thing, but with the numbers 1 and 0 instead. Okay, so for part A, again, we can choose a general 2x2 matrix, A, B, C, D, and we know that for singular matrices, the determinant is going to be equal to 0, so we have AD take away BC being equal to 0, which means that AD is equal to BC. Now, the only real way to do this question is to go through all of the different possibilities for AD and BC, knowing that they all have to be either 1 or minus 1. I've just taken the answers here from the solution bank, and you should end up with 8. And for part B, it's a similar sort of job, but with 0 and 1. And these are the answers from the solution bank for part B. It's nice and simple, not much thought really here. And finally, for mixed exercise 6, given that A and B are 2x2 matrices, prove that the determinant of A and B is equal to the determinant of A times the determinant of B. So again, a very, very similar starting point to the other two questions. We can begin with saying A is the general 2x2 matrix A, B, C, D, and B is E, F, G, H. So you'll notice that's a common theme with lots of these matrices, kind of proofs, starting with general matrices, so we can prove that it's true for all the matrices A and B. Okay, and now just working out what A times B is. So you should get that as A times E plus B times G, and then A times F plus B times H C times E plus D times G, and C times F plus D times H. Now, we want to prove that the determinant of this is equal to the determinant of A times the determinant of B. So if we work out what the determinant of AB is, it's going to be AE plus BG times CF plus DH minus AF plus BH times CE plus DG. And now we can work out what the right hand side is and compare. So the determinant of A is equal to AD minus BC, and the determinant of B is equal to EH minus FG. And if we multiply these together, we get AD minus BC times EH minus FG. So now if we return to the determinant of AB here, we're aiming for something that looks like this. This is the determinant of A times the determinant of B. So we're aiming to simplify this down to look something like what we've got up there. So the only way we can really go from here is to expand the brackets. So first off, we have AECF plus AEDH plus BGCF plus BGDH. Then we're going to have minus AFCE minus AFDG minus BHCE minus BHDG. And hopefully you can see some of these terms will cancel, like BGDH here and BHDG are the same, because the order that we multiply constants in doesn't matter. And the same thing happens with AECF here and AFCE. So we're just left with AEDH plus BGCF minus AFDG minus BHCE. And once again, returning back to what we have in the top right corner here, if we expand this, we have ADEH minus ADFG minus BCEH, and then the minus BC and the minus FG give us BCFH. Now, if we slightly rearrange this expression and rearrange the constants in each of these terms, then we can see we end up with ADEH plus BGCF minus AFDG minus BHCE, which is equal to the determinant of A times B as required. And that is the end of this challenge question walkthrough for chapter 6. I hope you enjoyed this video, and I'll see you soon.